Started with our next session, which is on semantics and types. I'm Sam Tobin-Hochstadt from Indiana University, and our first speaker is Garrett Morris from University of Kansas, who's going to tell us about partial type constructors. Take it away, Garrett.
Right, everyone hear me? Cool. So I'll tell you about partial type constructors. This is some work I've done with Mark Jones and Richard Eisenberg. As with any good talk, it starts out with a bad kids joke. So I want to start out by asking, when is a type not a type, right? Of course, when it's a jar. But more importantly, I want to ask, when is this type expression not denote an actual type, right? And of course, there are a number of ways this can happen. So it could be misspelled or ill-scoped, right? So struct point x is fine. There's an invisible green check mark here. Struct potin x, not so fine. There's an invisible red x there. And so if you're talking about a language like C or Java or C# pre-generic or something like that, that's about the level of type validation that you get. But we could also have types that are misapplied, right? Arity kinds of errors. So val x of type int list might be cool, right? But we're not allowed to just say val x of type list, right? List has arity 1, we need to give it at least one argument. So if you're thinking about like sort of old versions of SML, for example, you might get this kind of error. When we get to a language like Haskell with constructor classes, of course, the type theorists were there long before the Haskellers, we start worrying about kind systems, right? So I'm allowed to say M, it can be a computation of monad state int list int, right? What does that mean? This is a computation. It's got some integer state, and it's got some non-determinism going on, and it's producing a value of type int. But I'm not allowed to say M is a value of type monad state int, right? Int here is not the right kind of thing. It doesn't have kind star to star. It's not a computation model. Of course, for Haskell, anything of kind star to star will do. So I can say that M is something of type monad state int ratio int, and that means that it's a computation with some integer state and whatever computational model ratio happens to mean. GHC likes it, so it must mean something. But of course, this is constructor classes, right? This is 1991 era Haskell. Modern Haskell is much more interesting than this. In modern Haskell, you also have to make sure that it's not a uarray int integer, right? Uarray int is fine. Uarray int integer is not okay, right? Okay. Anybody have any questions on this slide? Okay. Well. To channel someone, lots of important people have asked me what's wrong with uarray int integer. So let's talk about the problem with uarray. So we have arrays in Haskell, right? We spell them with square brackets. Thank you. We also have real arrays in Haskell. We spell them array. And so if I describe a type like array int double, what that means, this by the way, this is the indexing type. This is an int indexed array. It's not really to do with the element type. This is an array of doubles. And so I have a chunk of memory, right? And in each memory, I have a double. And in Haskell, right, everything gets boxed. So a double, this means a pointer to some chunk of memory that has a double in it. Okay? And this will behave the way we expect things to behave in Haskell. It's all very fun. But you might be thinking about this, well, that's not really what I mean by an array of doubles. What I mean by an array of doubles is 4 doubles, for example, in a row, next to each other in memory. And we can do that in Haskell, too. So we call these unboxed arrays, or uarrays. So I'm going to declare a uarray int double, and this looks like this. It looks like 4 doubles in a row right next to each other. Now what's going on here? So this double, by the way, this isn't an unboxed type, right? So compilers like GHC have an idea of types that aren't boxed, and they have hashes in their names. This is not an unboxed type, but it is a type that GHC knows how to unbox, right? So GHC knows that a double is really, let's say, a d-hash constructor applied to a double hash value, and so it can put a bunch of double hash values next to each other, and it can handle the boxing and unboxing for us. So because GHC knows how to unbox doubles, we can build this thing. But GHC doesn't know how to unbox integers, or say int arrow int functions, or lists of int. And in a lot of cases, sort of unboxing those things would be meaningless. So a type like uarray int integer, where this is something that GHC doesn't know how to unbox, it doesn't make sense, right? It's a nonsense type. It's a description of something that the compiler can't do, okay? And I want to distinguish between this briefly and like empty types, because empty types are cool. We all like empty types. They're the units of sums. They do good things. This isn't, maybe it only contains divergence, but it's more than that. It indicates a sort of conceptual error on the programmer's part. My argument, there's an invisible red box around this pointing to that. My argument is that we should think about uarray int as a partial type constructor, right? Whereas list, or array int, you put a type here, you get a type back. Like array int is a total type constructor, takes stars to stars. Uarray int is a partial type constructor. You give it some types, int, double, float, word 8, you get a type back. You give it other types, integer, int arrow int, so forth, you don't get a type back, right? Now, that's fine, right? So what's wrong with that, right? I mean, we have these things in Haskell today. You write this, it's nonsense, it contains divergence, it doesn't get in anybody's way, okay? I'm going to claim this actually is a problem. And it gets in the way of the thing that makes Haskell really great. And the thing that makes Haskell really great for me is abstraction. So let's talk about mapping functions over collections, right? So I can, if I have a list of integers, I can map +1 across it, right? I spell that fmap +1, and I get a list of integers back, right? That makes sense. And if I have an array of integers, then I can fmap +1 across it, and I get an array of integers back, right? And that makes sense. And what's really nice here is I have this fmap abstraction, which I'm using in each of these cases. And if I have a u-array of integers, then I can map, and I get a u-array of integers, right? And so continuing the kids' jokes thing, does anybody spot the difference? Right? So u-array, it looks like a functor. It looks like we can do functory sorts of things to it, but it's not a functor. And now some of you out there may be thinking, well, this is just because GHC is mean, right? GHC has a whole thing about telling you that you're not allowed to do things that you want to do. But the reason GHC says this isn't a functor is that as far as Haskell understands the idea of functor, it's really not. And I can show you why. Let's imagine it were, right? What could we do with it? Well, let's map more functions across collections, right? So fmap from integral, right? It takes a list of ints and it gives us a list of integers back. And it's a nice list of integers, right? It's got the same size as the input list. It's got sort of roughly corresponding elements. If there's some divergence in here, there's some divergence in there, but not otherwise, and so forth, right? And I can fmap from integral across an array of ints, and I get an array of integers back, and the same sort of properties apply, right? The length of the input array is the length of the output array, and so forth. And if u-arrays were functors, right, then I could fmap from integral across a u-array, and I would take this thing, which presumably has a length and values in it, and all those sorts of useful things, and I get back nonsense, right? And that's the sort of thing that we really don't want fmap to do. Fmap is supposed to preserve structure, not destroy it, okay? My argument here is that as Haskell understands the idea of functors, this thing really isn't a functor. Now, this work is about saying, well, what if it were a functor? What if we change our understanding of these things just enough that we could make it a functor and that we could make this work? I'm going to spend most of the rest of the talk on that, but I want to take a brief moment out to say, some of you out there are probably thinking, I do not care about u-arrays, right? And you cannot say anything that will make me care about u-arrays. Well, luckily for you, I've got a whole slide of other things that are also partial type constructors. And it was kind of fun writing this paper because this list kept getting longer. Right? Every time we'd have another Skype call about this paper, we'd have another example of something that's actually a partial type constructor. So there's lots of collection types out there, right? U-array is one of them. Binary search tree is another. I don't talk about binary search tree because people start telling me that I should be working in a different category, but I'll be talking about it for a bit later. Haskell's got these cool numeric types, right? Like it's got int and integer and double, and then it's got things like ratio and complex. And so a ratio of ints, is a ratio built out of integers, and a ratio of booleans is something, and a complex built out of string concatenators is something else. I don't know, but Haskell's happy with them, right? That seems cool. Monad transformers, same problem I was arguing earlier. What computational model is ratio here? I mean, Haskell's happy with this. It claims this is a type, but what does it mean, right? We have type functions. So we have like an element function. It gives you sort of the elements of a container type, like element of list of A is A, element of BST of A is A, element of bool is something, I don't know, element of a tuple. This is probably actually bool because of some sort of traversable nonsense. But, and there are lots of other things that people have wanted to do, right? Unpointed types a la Launchbury and Patterson, and also actually people in the audience. Various representation concerns. There are actually a fair number of these things running around that are partial. And well, a lot of these only cause minor irritants, right? Like, what's the consequence of this? Well, it means that you get this silly monad M constraint on everything that ever talks about a monad transformer, right? So monad transformer, it's never monad state int M something. It's always monad M implies monad state int M something, right? I already said monad state. It's a monad transformer. I'm really not interested in how it transforms not monads, but that's fine, right? That's just an extra constraint. The things that really bug me are the sort of the things we can't make functors, right? The things we can't make monads, the things that don't play well enough with our abstractions because we don't know enough about them, okay? So this talk is about embracing partiality, right? What if we sort of went back and said, you know what, partial type constructors are cool. Let's have partial type constructors. Let's even assume that type constructors are partial by default. What goes wrong? What happens? What kind of language do we get? We wrote a paper about it, which I hope you'll be able to read in its final version soon. It's got 3 parts, right? We build what I call a practical uniform type system with partial type constructors. Now, there are lots of encodings to deal with partial type constructors in Haskell, and they're very clever. I'll talk about some of them at the end. One of the things they all have in common, though, is they're all specific to particular use cases or specific to particular sort of views of how we should represent partial type constructors. And they're specific to assumptions that we already didn't make when we described what the functor class meant, right? Our goal is to have something where we don't have to go back and rewrite everything back and rethink of everything. We can just give all of these things a uniform treatment. We give a translation from partial type constructors to a language with total type constructors, right? So we can give these things meaning in sort of the kind of type theory that we know and love. We have to incorporate evidence in types and predicates and kinds to capture this partiality, right? And we did an experimental analysis showing that this really doesn't seem to have that much impact on existing Haskell code for the correct definitions of minimal, impact, and existing, all right? So most of this talk is going to focus on the first bullet point. I've got a bunch of slides on these that I'll flip through while complaining that I don't have enough time. If you want to find the draft paper, it's available online. So here's the crux of the problem, right? Here's the key challenge. How do we know when one of these types is actually defined, right? So let's talk about binary search trees for a moment. But a binary search tree over some type like, over some type A makes sense if that type A has an ordering. And it doesn't make sense otherwise, right? So this type BSTA, let's get the invisible checkmark and X up here. This type BSTA kind of makes sense, right? BST int makes sense. We know how to order ints, so we can build a search tree of them. This type BST int arrow int doesn't make as much sense, right? I mean, we might be able to conceptually talk about how to order int arrow int functions, but it takes a long time, and so Haskell doesn't give us that instance. So this is good. That's bad. And now what about this type, right? What if I tell you, you tell me a functor f, and I'm going to build you an f of int? Does that make sense? Well, it seems to for BST. Might do for UArray. I can probably imagine a functor for which it doesn't. So what are we supposed to say here? Right? We identify basically this as being the source of all the complexity in this system, right? We don't have generic, types don't sort of magically stop existing. What we have are type constructors, like f here, which may be applied to arguments outside their domain. And so that's exactly where we're going to add a little bit of stuff. We're going to add a new predicate, f at t, which basically means f is applicable to t, right? And this is going to fit into the existing Haskell predicate logic, so this sort of works well in Haskell. But you could imagine adapting this to sort of almost any other approach to typing. And we're going to define this predicate to hold sometimes and not otherwise, right? So we're going to say BST at int holds. We're going to say that we cannot prove not entails BST at int arrow int. And in general, we're going to say that the idea ord A has an ordering, and BST at A are sort of interprovable, right? If you can prove that, you can prove this. If you can prove this, you can prove that, all right? That's sort of the key rule. So this captures exactly the cases where type can be undefined, right? You don't have to prove that int is a type, right? You don't have to, but you do have to prove that BSTA is a type. This naturally incorporates total type constructors, right? So I can just say, hey, it's always provable that list is defined at A, right? And all of my total type constructors will just work, right? Those constraints will just go to say arrow A. It's always defined, it's defined for arbitrary B. Okay, so we naturally incorporate total type constructors. And then we want to integrate this into our kinding relation, right? We want to say that well-kinded types have to actually be well-defined. So BST int, for example, that has kind star because we can BST at int. BST int arrow int does not have kind star, right? Doesn't have any kind at all because we can't prove BST at int arrow int. More importantly, this thing, functor f implies f of int, that doesn't have a kind either because we don't know enough about f to know whether f is actually applicable at type int, right? What we have to say instead is, well, I'll tell you it's a functor and I'll tell you it works at integers. And we know that it has type star, all right? You might be thinking, this is a little redundant, isn't it? Hold that thought. I agree. I'll come back to it. How do we figure out when a type is partial? Well, we can just declare it, right? So you write data ord A implies BSTA, and you give some constructors for it. We can derive the entailment relation I already showed you from this definition. Keep in mind, this is not the same as a GADT, right? It may look like a GADT, but there's a key difference in the understanding. For a GADT, you would say, well, BST int arrow int, for example, is perfectly good type. It's just empty. I mean, it contains divergence. That's as close as we can get in Haskell. Here, we say BST int arrow really doesn't exist. It's not a type. You can't talk about it at all. Historical note, This restores data context to their meaning in Haskell 1.0. If I have time, I'll sort of show you a bit of ancient Haskell report when we get to the end of this. So here's my functor class, right? What do functors have? They have an fmap method. What's fmap do? It takes an a to b function and an fa and gives you back an fb. And now I'm going to be careful and say, well, you know, we have to make sure that f is meaningful at a. We have to make sure that f is meaningful at b. I said something early on about not having to have anticipated this. And so what we do is we actually say, you know, there are a bunch of constraints that you might have to write down formally, but we can really figure out what those constraints are. I mean, first of all, we actually have to know, for example, when we wrote down this type A arrow B, right, that, you know, arrow at A was meaningful, right? It's meaningful at type star to star. That arrow A, assuming that was meaningful at type star to star, is meaningful given an argument of type B. We always know that, right? Arrow is a total type function. So we can sort of discharge those constraints immediately. We can sort of discharge it. We can exactly discharge it immediately. But we can also do some sensible elaboration, right? Anytime you write a type application FA, we're going to assume that you meant for that to be meaningful, right? That you didn't write f of a because you were sort of in a funny mood, that you meant f of a because you wanted that to be a type. And so whenever we see that, we'll automatically elaborate it into the constraint f at t implies f of t. So these two constraints right here, they go away. And in our system, this is how you write the functor class, right? You say you have a type f as a functor if the f map takes an a or b and an f of a to an f of b, right? So we have no apparent change to the meaning of functor, right? I've said apparent because we've had to rethink what we mean by the implicit star arrow star here. But having done that, having adjusted our mindset, we have no change to the text of the program. But now we can do things like making uArrayInt an instance of functor, and it behaves the way we want it to, right? We can still fmap from integral across arrays of ints, or I'm sorry, across lists of ints. I thought that thing about skipping slides was a joke. And get lists of integers back, because list is defined at all types. List of integers is perfectly reasonable. But if I try to fmap from integral across a uArrayInt int, this doesn't type, right? Why doesn't this type? Because to instantiate this type, I need to satisfy the implicit f at b constraint, and that constraint's not satisfiable. So you try to write this, you'll get an error that says, by the way, uArrayInt doesn't work at integer. It's exactly the error you want. Now, there are places where you still need this, right? Here's sort written using the API of a binary search tree I haven't showed you. And what do you know? You have to say BSTs work at A's. How do you know that? Because BSTA doesn't show up in the type anywhere, right? We take a list of arguments, we give you back a list of arguments, nothing in there about BSTs. So if you're going to use a BST internally, you ought to announce that. But here's the thing. You already really needed to say that lists were ordered for sort to make sense, and ORDA was sufficient to prove BSTA, right? So this type, the one you would sensibly have written anyway, is the one that works. OK, you might have some more questions. You might want to know about the translation from this language to a language with total type constructors. But Sam's waving fingers at me. So what I will tell you is it's in the paper. It makes sense. It's mostly what you would expect. It gets convoluted. And the reason I'm stopping on this slide is not to say, oh, look at this terrible type. I mean, it's kind of terrible. We could walk through it. But to say, you might be thinking, why not just encode this stuff, right? Why do we need a language extension? Why not just use an encoding? And this is my answer. This is the translation of this thing, right? Now, I like this type because I came up with it. Well, because I helped come up with it, because Richard came up with it. But I don't want to write it. And I certainly don't want to try to program with it. But we have nice meta-theoretic results. Our intermediate language is type safe, and we have a type-preserving translation from the surface of the intermediate language. Finally, I said, you know, elaboration can automatically add most of these definiteness constraints. And I'm assuming that most of you heard that as look forward to rewriting every type signature in your programs. But that's actually not the case. We did a small experiment. We modified Hughes to enforce at constraints in existing Haskell code. And then we tested it on a bunch of the standard libraries. Why do I think the Hughes standard libraries are a valid test case? And what Hughes compiles. But also, they're full of polymorphism, right? Where this stuff bites is not when you have a bunch of monomorphic types and you have a bunch of like fully applied BSD int running around, because we can discharge all the constraints there. Where this bites, where you have to add more constraints, is where you've got these type variables, where you've got type variables running around. So we're including, you know, MTL, we're including arrows, we're including these sorts of complicated types. So yeah, the majority of code is unchanged. We had a couple of interesting cases. So like this map and unzip function gets a constraint that we didn't necessarily expect, that the monad M is applicable to this type list of BC tuples. The fun thing about that is that that's an artifact of the way a map and unzip is written. If we rewrite it as a fold, then that goes away. Now, this is not necessarily good. We'd like to write this the first way, but there's something sort of interesting going on there. We had one really weird case. The good news is nobody's ever used it, so I don't think it's a problem. So yeah, so we think it's not unreasonable in practice. Time? Okay, let me tell you about a couple of things that are related. So John Hughes had roughly this idea roughly 20 years ago. He wanted to do it like this. He wanted to say that this collection, for example, the collection class C should take an additional parameter context, right? And he's going to write stat of context in front of every type. So you need to explicitly parameterize classes. So one of the other things about this is that this sort of requires the person who is coming up with the functor class, for example, to assume that it would be useful to have this context around. We think the weight should be the other place. It should be on the data type declaration to announce its partiality and for the applicant and for the sort of abstractions to adapt to it. Hughes also argued for these constraints to be explicit. He really didn't want to be inferring any of these constraints. That programmers would be surprised if these constraints were inferred. And again, we think that sort of betrays a mindset that total type constructors are really the default, and we sort of disagree with that. Constraint kinds can be used to realize Hughes' system almost directly. So you can do this in Haskell. But back to my argument about the type of fmap, right? We can do it explicitly. We just really shouldn't want to. Haskell 1.0 has this fantastic description of these type and data contexts, and it says, the context portion of these declarations declares that a type is valid only when this context holds. And their example is, look, we have a type alias for points, but it's only defined for numeric things, right? This is a really cool paragraph. There's an email from Simon PJ a little bit later. Nobody has been able to give a satisfactory account of what context and data and type declarations actually mean. And so if you look in the source code of GHC right now, these contexts are still around on data declarations, and the variable in the GHC source code that stores it is called stupid theta. We think we've given them back the meaning that the designers of Haskell wanted them to have all along, and it's kind of a pity that Phil's not here to hear that. These kinds of things arise in OO languages with generics. And so for Java, they're not super interesting. For a language like Scala, they're much more interesting. And there's sort of a recent PhD thesis that's tackling a kind of similar problem, but again, in a more explicit setting. The real difference here is a sort of usual trade-off between subtypes and qualified types. In particular, sort of we get all the type inference properties that you would expect for a qualified type system for free, while for subtyping and bounded polymorphism, those aren't necessarily even sensible things to say. All right? You might have some questions. Luckily, I put a draft paper online, so that should sort all of that out. And if the next speaker's around, I'm done. Yes, but you have to take a suitably expansive vision of what my work means. So I would say there actually is probably closer to the constrained type families work that Richard Eisenberg and I presented at ICFP a couple of years back. Type synonyms are really kind of like degenerate type families, right? They're like type families with a single defining instance. And so our work on constrained type families would give you what you want there.
More questions?
All right, thanks, y'all.
Thank you for